The von Mises stress equation, or the distortional energy failure theory, takes on many forms that are convenient for particular situations. This general form right here works for any stress state. The challenge with this form is that sigma 1 and sigma 2 and sigma 3 are the principal stresses. So if considering a standard stress element, we need to compute the principal stresses in order to use this von Mises stress equation. If we have a biaxial stress state where one of the three principal stresses is 0, the sigma prime, the von Mises stress, can be expressed as this expression here. And the nice thing about this expression is that sigma x, sigma y, and tau xy are simply the stresses on your stress element. They are not principal stresses. And so this form of the expression is very handy and is a great simplification when we go to a biaxial stress state. Now if sigma y in this equation here is also 0, which is often the case in many beam situations, we see that this equation reduces further to sigma x squared plus 3 tau xy squared, quantity square rooted. So you should also commit this equation here to memory. So you should memorize this general equation that works for any stress state, and then for a biaxial stress state where sigma y is also 0, you should commit this equation to memory. For pure torsion, we have the case where sigma 1 equals sigma 3 and sigma 2 is equal to 0 and tau is equal to sigma 1. And in that case, then we can see that this reduces to tau is equal to 0.577 SY. And recall for maximum normal or maximum shear stress, we had tau is equal to 0.5 SY. So plotting this expression for our safety factor equation as given here, letting our safety factor equal 1 and plotting that expression, we get what we call the von Mises ellipse. We get this ellipse right here. And you can see how good of a fit this von Mises ellipse gets with experimental data. Right here, the experimental data pretty well straddle the von Mises ellipse line, and also through here, the experimental data pretty well straddle the von Mises ellipse line. Also superimposed on this plot is the maximum shear stress theory, and we can see how it fits inside the von Mises ellipse envelope. So this is the most accurate failure theory for ductile materials, where the shear strength the strength in tension and strength in compression are equal. And so from now on, in all of our problems, you should use distortional energy as your failure theory of choice, given that it fits the right situation. So as a review, this is a critical equation to remember for a biaxial stress state when sigma y equals 0. And this is a critical equation to memorize that represents the von Mises stress at any stress state. And here we have our safety factor equation, which is essentially the yield strength Sy divided by our von Mises stress. Hello, and welcome to another lecture for Machine Design, Mechanical Engineering, ME 372. In this lecture, we're going to review static failure theories and the material that we covered in the previous lecture. We will then continue by talking about the ductile Coulomb-Moore failure theory, and then we'll work an example problem using all the failure theories we've talked about, and then we'll discuss a flowchart that will help us decide which failure theory is most appropriate. So, in review, we talked about ductile material failure theories, and we decided that ductile materials were determined by a strain at fracture of less than 0.05. So if your strain at fracture is less than or equal to 0.05, your material will be a brittle material. If your strain at fracture is greater than 0.05, you have a ductile material. And you need to make sure that you apply this idea to the material under the conditions of which it will be used in the application that you are considering. For example, many ductile steels act as ductile materials when the temperature is room temperature and above. But if the temperature gets so low, these ductile steels can actually act as brittle materials, and the brittle material failure theory should be considered and used in those situations. So the ductile material failure theories we're going to consider are the maximum shear stress, distortional energy, which also goes by the name of shear energy, von Mises-Henke, and octahedral shear stress, and then ductile Coulomb-Moore. Then the brittle materials are the maximum normal stress, and we talked about that one. And then there's brittle Coulomb-Moore and modified Moore. So just as a quick review of the maximum normal stress, we realize that this is probably the failure theory that you have used up to now, where we essentially consider the largest principal stress and compare that to the yield strength in tension. Or we take the minimum principal stress and compare that to the yield strength in compression. And we realize that this failure theory is okay if sigma 1 and sigma 3 are both positive. But if sigma 3 is negative and sigma 1 is positive, such that we have a fair amount of shear in the situation, then this failure theory can overpredict the actual strength of the material. We need to also remember that we always rank our stresses as sigma 1 as the rightmost principal stress, sigma 3 as the leftmost principal stress. We remember that the failure envelope for the maximum normal stress theory looks like this square box. And we see here that it's a conservative method, but when sigma 1 is positive and sigma 3 is in compression, we have a negative. This here is listed as sigma 2, but it should represent sigma 3, or the leftmost principal stress. We then talked about the maximum shear stress theory, and we decided that this failure theory was based on computing the maximum shear in the stress element. And so what we do is we take a tensile stress member and we compute the stress when the principal stress in this tensile member is equal to the yield strength. Then we take the shear stress at that point, and that's the maximum allowable shear stress in our element. So it's somewhat based on a principal normal stress idea, but we're looking at it in terms of a shear representation. So it says yielding begins when the maximum shearing stress at the point of interest reaches a value equal to the maximum shearing stress in a tension specimen when yielding starts. So we come here and we know that yielding will start when we hit sigma 1. And so we compute the maximum shear at that point, and that's tau max. And we take that value and compare it to the yield strength of our material. So in a tension test, tau max is sigma 1 minus sigma 3 divided by 2. And we get that from this stress element, where when we pull on this in tension, this would be the stress element we get. Plotting our vertical point, we'd have point 0, 0, and then our horizontal point would be sigma, 0, giving our origin of planes right here. Our sigma 1 then comes out to here, and the radius of this circle is half of sigma 1. So we get tau max is sigma 1 divided by 2. We replace the sigma 1 with the SY and get tau max is SY over 2, and we call that SSY. We now write our failure envelope equation as safety factor eta is equal to SSY over tau max. And we know tau max is this expression here. We know SSY is equal to SY over 2, and so I can write my safety factor expression as any of these four forms of the equation, or represented by these equations. So we note here that the shear max is given by 0.5 SY, whereas with distortional energy, the better answer is 0.577 SY. So plotting the failure envelope for maximum shear stress, we get this shape of our failure envelope, and we see that this dashed curve is predominantly on the inside of all our points, indicating that this is a conservative failure theory. So that's a nice feature about the maximum shear stress, and it's also a nice feature that this failure theory is very easy to apply. We then talked about distortional energy, and we decided that the distortional energy failure theory is based on the energy caused to distort the element. We recall the discussion where researchers found that by putting the member in hydrostatic pressure, where the pressure was equal in all directions, that caused a volume change, but it did not cause a failure. And so what we need to do is take our total strain energy and break it into the distortional energy component and the volume strain energy component. And we actually need to solve for the distortional energy because it's the distortional strain energy that causes failure. The volume strain energy does not cause failure. And so to separate this out, we haul the volume strain energy to the other side, and we compute the U total and the U volume. And then from that, we can compute the distortional strain energy. And we went through these expressions and came up with this expression here for the distortional strain energy. And this expression is based on Poisson's ratio nu, modulus of elasticity E, and then these three principal stresses. Continuing on with the development, we came up with the safety factor expression as given here, where the safety factor is SY over sigma 1 minus 2 quantity squared and so forth, which we called sigma prime, or the von Mises stress. And sigma prime then is given by this expression here, and this is certainly an expression that you should commit to memory. We then looked at various stress states for this particular failure theory, and if we have a biaxial stress state, we see that we can represent sigma 1, 2, and 3 in terms of an X, Y, and a shear, and the XYs are not principal stresses. So it's a great simplification to have a biaxial stress state, because we now no longer have to compute the principal stresses to compute the von Mises stress. Then if sigma y in the biaxial stress state happens to be 0, which is the case in many, many beam situations, we get sigma prime is the square root of sigma x squared plus 3 tau xy squared. For pure torsion, we see that this is 0.577 sy. So this is a super important equation, and we'll use it throughout the remainder of the course, as well as this equation here. When we plot the failure envelope, safety factor equal to 1, we get this von Mises ellipse, and we see how well it fits the experimental data, where this is the experimental data that has been used in the other plots. We now want to talk about a failure theory that doesn't require the tensile yield strength and the compressive yield strength to be equal in magnitude. That's the one downfall with the von Mises distortional energy failure theory, is that the tensile yield strength and the compressive yield strength must be equal. So we're going to look at this failure theory that's called the Coulomb-Moore failure theory for ductile materials, or it's often called ductile Coulomb-Moore. In the distortional energy and maximum shear stress failure theories, the tensile and compressive yield strengths must be equal. In many materials, this is not the case. For example, in magnesium alloys, the compressive yield strength can be as little as 50% of the tensile strength. And for gray cast iron, this is the opposite, where the compressive strength can be up to 4 times the ultimate tensile strength. So in the early 1900s, Moore, and this is the same Moore that did the Moore circle. So this is Christian Otto Moore, who I believe now is a member of the church, recognized this and developed a failure theory for materials where the tensile and compressive strengths are not equal. He developed a failure envelope by testing the material in tension, shear, and compression, and he obtained a Moore circle for each test as shown below. So you can see that the left circle represents the Moore circle for the compression test, the right circle for the tension test, and the middle circle for the shear test. He then plotted lines tangent to each circle as shown by the line ABCDE, and this line became the failure envelope. The idea is that the user would plot the actual Moore circle for the part being analyzed, and the loads could be increased until the Moore circle for the part became tangent to the line ABCDE. So to restate this, what Moore did is he took a tension specimen and he put it in a compression test, and he computed the Moore circle for the tension test, where this would be the compressive yield strength. Then he put the specimen in a tension test and he pulled on it, and he measured the tensile yield strength. And then he did a shear test and he put the member in pure shear, and he got this middle circle here. And then he draws this ABCDE line, and then he takes the Moore circle for the part of interest, and say the Moore circle for the part of interest has some tension, it has some compression, and so that my Moore circle would be somewhere in this region, and then he lets that circle grow by increasing the stresses until it becomes tangent to this line ABCDE. And this theory works really well. It does a good job, but it's pretty hard sometimes to get this middle circle where we have pure shear. And so this is where Coulomb came in and modified the theory and said, let's get rid of this shear circle and just combine the compression and the tensile test circles with one straight line. And so the Coulomb portion of this is to get rid of the shear and just take the compression test and the tension test and get one straight line here. And the equation for this one straight line can be expressed as sigma 1 over St, where St is the tensile yield strength, minus sigma 3 over Sc, where Sc is the compressive yield strength, is equal to 1 over N, where N is the safety factor. And then for plane stress, the two non-zero principal stresses are sigma A and sigma B. And the same three cases discussed for the maximum shear stress theory can be used here to plot the failure envelope. And the results showing the ductile Coulomb-Moore failure theory is shown below. So what we get is an angle line here in our quadrant 4 and in our quadrant 2. Over here in quadrant 1, we just have our regular box. So this looks an awful lot like the maximum shear stress theory, and we have essentially the same shape of our envelope, except now our compressive yield strength is much bigger than our tensile yield strength. So associated with the Coulomb-Moore failure theory, I will expect you to be able to explain how it was derived and how Coulomb simplified the theory. And then this equation here, we need to make sure we know this expression that represents the failure envelope. So in summary of the methods, if we let the tensile yield and the compressive yield be equal, we have the maximum shear stress theory. It's given by safety factors Sy over sigma 1 minus sigma 3, where sigma 1 and 3 are principal stresses. Sigma 1's the rightmost, sigma 3's the leftmost, and then we have tau max with SSY. And this predicts yield at SSY is 0.5 SY. And this theory is conservative. We then talked about the distortional energy and how we decided that researchers found that it's the distortional energy and not the volumetric strain energy that causes failure. And so our safety factor equation for distortional energy is Sy over sigma prime, where sigma prime is given by this expression using our principal stresses. And this theory has several names: distortional energy, von Mises, strain energy, octahedral shear stress, and there's probably some others. And then we had the method that we just talked about, the ductile Coulomb-Moore method. So if we look at static failure, a static failure example, here we have a machine element and it's loaded as shown so that we have these Moore circles. The material has a minimum yield strength and tension and compression of 60 kpsi, and it says find the factor of safety for each of the following failure theories. And we look at the maximum normal stress, so we rank our principal stresses. Here's the answers that we get after ranking them. We see that we have a large positive tensile and a relatively large compressive. So we know that we're going to be in the region where this maximum normal stress theory is bad. And so we can expect a large overprediction of the result. So coming down here, our safety factor equation is given by SYT over sigma 1 because sigma 1 is our largest principal stress. Otherwise, if this would have been our largest principal stress, we would have taken this value over and compared it to the compressive yield strength. But since the 20 is larger than the 15, we take the 60,000, which was given as the yield strength, divided by the 20, which gives us a safety factor of 3. We then look at the maximum shear stress theory for this case, and we know that this stress theory will likely underpredict and be a conservative response. So here we have Sy over sigma 1 minus sigma 3, SSY over tau max, So I have the 60 over the 20 minus a negative 15 gives me a 1.71. And we know that this is likely at least that large of a safety factor, and probably more based on the conditions of being in tension and compression with our stress state. So now we'll look at the distortional energy failure theory. We have Sy over sigma prime. We plug in our values to that equation. We get our sigma prime. Then we look at our safety factor, and it tells us we have a 197. So comparing the three safety factors, we get 3, 171, and 197. These results make sense because this is a case where the shear stress is high. So it is known that the maximum normal stress theory is wrong and overpredicts the safety. Maximum shear stress theory is conservative, and distortional energy theory is the most accurate result. So hopefully that gives you an example problem that you can use to better understand these failure theories. The last thing we want to look at is this slide that helps us select the appropriate failure theory. So the first thing to do is to come and look at the strain at failure. So epsilon F here represents the strain at fracture or strain at failure. And if we're less than 0.05, we are a brittle material, and we would come down and look at if we want to be conservative. And if we want to be conservative, we'd use the brittle Coulomb-Moore theory. If we didn't want to be conservative and closer, we'd use the modified Moore failure theory. Then, if we want to look at the ductile side, where our strain would be greater than 0.05, we'd come over and would say, is our tensile and compressive yield strengths equal to each other? And if they are equal, we can come over here, and if we want to be conservative, we'd use the maximum shear stress theory. If we wanted to be more accurate, but not necessarily conservative, we would use distortional energy. And then way back up here in this decision block, if our SYT and our SYC are not equal, then we would come over and use the ductile Coulomb-Moore. So I will expect you to be able to go through this decision chart and write this decision chart down. You should essentially be able to redraw this decision chart, and then you need to be able to write down the failure theories for the ductile Coulomb-Moore, the distortional energy, and the maximum shear stress. You need to be able to describe how each of these three methods is derived and the theory behind it, and you need to be able to use these three different failure theories appropriately given initial stress conditions. So hopefully this gives you a good review